Welcome. This is going to be a fun event. I am Dr. Cameron Hummels. I am a computational astrophysicist at Caltech in the astronomy department, and I will be your MC for this evening's event. We've got two super awesome talks from two super awesome people tonight, and then we've got pub trivia. If this is your first time, just a kind of general schedule for what to expect. After a couple of announcements over the next couple of minutes, I will invite our speakers on. We'll kind of chit chat for a couple of minutes, and then we will have a 15-minute informal talk about the first stars in the universe from Evan Nunez, followed by Q&A for 5 or 10 minutes, depending on how many questions you guys have. And then we will immediately go to our next speaker, Rebecca Larson, who will be talking about the first galaxies in the universe for about 15 minutes, and then 5 or 10 minutes afterwards for Q&A from you guys. We are streaming this both over YouTube Live as well as over Facebook Live. So I encourage you to ask questions in the comment section below this, my waving head here, either during the presentation or after the presentation, and I'll scout through them and pick out good questions and ask them of our speakers. And then following all of that, which should take roughly an hour, we will have pub trivia that's interactive, where you guys can connect to a website and get the questions along with as we ask them on here. And then when you type in your responses, it'll pop up on our screen and you'll see how you're doing relative to other people. So it's super fun. They're all astronomically themed questions, and some about current events in astronomy and some about just general astronomy and space science. So super fun, and I encourage you guys to stick around. Our Astronomy on Tap events happen about once a month, but our next one is going to be in 2 weeks' time, and it's going to be all about weird telescopes. So we'll have one talk that's about the Sophia telescope aboard a 747 jet that goes up at night up above most of the atmosphere and takes pictures of the sky, and one about a planned telescope called the Lunar Crater Radio Telescope that's being planned to be built on the far side of the moon in a lunar crater, which is super awesome. So that is, 2 weeks from today. I forget the exact date. I think May 10th. And we have a sister series of events called the Caltech Astronomy Stargazing Lectures, which happen once a month. Our next one of those is about a month from now on a Friday night, and it'll be about neutron stars. And I'll be posting more information about that on our website and on YouTube and so on and so forth soon. So I think those are all of my announcements for now. Evan and Rebecca, do you guys want to join me here?
I would love to join you there.
Welcome.
Absolutely.
So this is Astronomy on Tap, which is traditionally held in a bar. We, of course, are not holding this in a bar right now. We're holding it from our homes on computers, but the drinking stays alive. What beverages are you guys consuming?
I have some high quality H2O this evening.
Ooh, I'm a big H2O myself.
We're a bit of a disappointment because I have iced coffee, but at least I have one of your pint glasses.
Swag pint glasses. That's very nice. I'm impressed because I don't even have one of those. I sold them all and I didn't keep one for myself. I need to.
You didn't even keep one? I might have two if you
Oh no, I'll make another batch and we'll get them. But yeah, that's one of the things that if people attend in person, we sell those not to make any money, but just to help support the event and pay for the prizes that we normally give out after the quiz. But unfortunately, there are no prizes right now. So
bragging rights are prizes.
Yes, thanks. Your prize is knowledge. Cool. Okay. Well, Evan, you're gonna go first. Is that right?
Indeed.
Okay. Sweet. All
Bye.
right. I will. We'll see you in a couple of minutes, Rebecca. Evan Hayes Nunez is a second-year graduate student studying astrophysics at Caltech. His work involves using rare objects to measure the metals that were ejected from the first stars. He loves science outreach and has been active in it since 2015 during his first year at community college. He's a Southern California native, avid music lover of both hip hop, jazz, rap, indie, alternative, bedroom pop, lo-fi beats. Ooh, bedroom pop. I want to hear more about that. A console gamer for both the PlayStation 4 and Switch, and he loves the outdoors in comfortable bursts. So wait, before we go on, what's bedroom pop? Because that sounds awesome.
Yeah, so I guess the the way that I would describe it is like the type of music that that's like kind of peppy, that you wouldn't necessarily play with your friends. You kind of play like in your room by yourself, just kind of like vibing out a little bit. So yeah, it's a very like mellow sort of pop type of sound is a good way to think about it.
Okay, that's cool.
Very vibey.
I dig it. Cool. Well, I will let you take it away. I'm excited to hear about the first stars, Evan.
Fantastic. Thank you for the introduction, Cameron. Hello, everyone. Very, very nice to be here. First off, I'd like to say hello to my mom, my little cousin, who's basically my little brother, my girlfriend, all the family and the good stuff, just because I can. And yeah, today we're going to be talking about the work that I've been working on here at Caltech, which is looking at the metals from the first stars. So for no reason at all, I wanted to kind of share that I gave a shorter version of this talk back in late October, during spooky season. And I kind of like the title. I called it The Alchemists Who Haunt Old Galaxies. And this is kind of relevant, and I'll talk about it a little bit later, but kind of cool. So this is Astron Tap, and I kind of thought it would be fun because I am going to talk about a little bit of physics today that I think it would be cool if I could kind of turn my talk into a drinking/hydrating game. Always got to keep the water. And so I would suggest whenever I say any of these three phrases or words, but whenever I say physics, whenever I say the phrase metal pour, or I say the word supernova, then I would suggest taking a drink. I wouldn't take very big drinks or very big swigs. It's just, I'm probably going to be saying this a lot. So, So with that, let's go ahead and jump into the metals from the first stars. So we first have to step back all the way, and you have to understand that in the beginning, there was hydrogen and helium and trace amounts of lithium. And what we as astronomers call metals is everything else outside of hydrogen and helium. And it sounds, for all the chemists that are out there, sorry, but the reason is because of this. What I'm showing here is the fraction of the mass of the sun. So in other words, when we look at the sun's mass, how much of it is hydrogen, how much of it is helium, and how much of it is the rest of the stuff. And so if we look at it for hydrogen, it makes up about 74% of the sun is hydrogen. For helium, it's about 25%, and the rest of it wakes up only 1%. And it's this 1% that I'm concerned with, that we all are concerned with, because carbon, as you can probably imagine, is very important for us. Silicon is very important for us. And so we want to figure out all of these elements that really do mean a lot to us, and even though they make up a very small fraction of the total mass. So where we have to start from here is, how do we actually go from a metal-free universe to a metal-rich universe? And that's where we are right now. And I kind of have to answer this in a little bit of a step process here. And so the short answer to the question is that metals were synthesized by nature's alchemists. So this first slide here is basically looking at what are the two differences, or like the two main components of a star in terms of like what's driving them. And so a star is basically a balance between two forces: nuclear pressure, or nuclear forces pushing outwards, and then gravity pushing inwards. And it's this nuclear fusion that is the true alchemy of the universe, where you have light elements being forged into heavy elements. Very simple. And the key here is that you have this outward force that's coming from the core of the star pushing out. So then there has to be a force that's balancing this, right? And yes. And the answer for that is gravity. So when we say gravity, I literally mean the actual mass of the star wanted to compress. And so you have this delicate balance between this nuclear fusion that's pushing out and this gravity that's pushing inwards. So in order for this fusion process to happen, you need to have very high temperatures and very high densities. And this is why this has to occur in the core of a star, because otherwise there are very few other places in the universe that we know of that you could get this happening. The only other ones are when you have the explosions of stars. So what you end up having is hydrogen being fused into helium, helium to carbon, so on and so forth. And if you have a massive enough star, you'll actually create these onion layers of all these elements. And that's actually what we're going to be seeing here. And so if your star is massive enough and you have all of these material and you have all of this newly synthesized material, all these reactions, right? Hydrogen to helium, helium to carbon, carbon to neon, so on and so forth. All of this stops once you get to iron. And the reason is because of the principle that I outlined previously, which is that you need some force that's pushing the star back outwards, right? Because gravity's trying to collapse it, but what's the force that's balancing that? It turns out that all of these processes up here end up, once you fuse hydrogen to helium, you get a little bit of energy from it. Well, not a little. I mean, well, okay, it's a little for our human standards, but once you add, billions, trillions of these reactions, and it's a bunch of energy. And so as a result, no big deal. But once you start to fuse silicon to nickel, technically, and then that decays to iron, you actually lose energy. And so you basically don't, unfortunately, at this point, you don't really have anything to support the star. And so this, unfortunately, marks the end of a massive star's life. And we're actually going to step through some of the physics of why this actually happens, or of what happens after this. So we're going to do a quick zoom in to the core of a star. So this is what we have here. This is the core of a massive star. And these boxes here, we're actually just zooming in. And at this point, you've already have silicon being fused into iron. And as I mentioned, there's no energy that's being, this is an endothermic reaction. There's no energy that's being put out from that. So these arrows are indicating that the core is literally collapsing. What ends up happening, though, is that for this particular star in particular, it's not massive enough for it to implode into a black hole. So you end up getting this bounce, and that's what these red arrows here are showing. The core is actually bouncing out. It turns out there's actually a subtlety within this that it's just not worth going over at the moment. If you're curious, I can let you know. But what ends up happening is this material bounces off the core and you end up getting yourself a supernova. And so this is why we call them core collapse supernovae, is because the core is literally collapsing on itself, bouncing back out, and bang, you have yourself a supernova. So this material ends up getting spread all across all these outer layers that we're seeing get ejected. And so this is a quick little animation, well, really an artist's impression of core collapse supernova happening. And for those of us that are in the amateur astronomy world, you'll actually know very clearly what this remnant is. And I'll just go ahead and let it play. It's very, very beautiful. All of this ionizing radiation, all of these metals that are being ejected. We have ourselves the Crab Nebula, which is very, 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 very cool. Very pretty to look at. So all that material that was in the outer layers of the star all gets ejected. And these are, what I'm showing here, are visual representations of this happening in our vicinity. So we actually observe these. So on the left is actually an amateur image of the movie that we just watched, except this is the actual image here. So this is the Crab Nebula taken by an amateur astronomer in Austria, where you're actually seeing over a decade, the remnant is expanding. For those that are curious, this is also called M1, Messier 1. This was the first object that Charles Messier put in his list of objects to stay away from because it wasn't a comet. So for him, this is like the epitome of another person's trash is another person's treasure. And on the right here, we have another supernova remnant. This is called Cas A. Both of them show these weird like tendril structures that are coming all over the place or that are ejecting and have all these shapes going from all over the place. And they're colored by the different elements that are present. So in the Crab Nebula on the left, what we're seeing in the red is hydrogen, as well as some helium. And if we had another image of this in the X-rays, we'd also see neon, oxygen, sulfur, all that good stuff. And on the right, we actually do have it color-coded as such. So this is a image from the Chandra X-ray Observatory, and it's colored. Gosh, I wish I could remember what the actual colors were, but either way, it's sulfur, iron, calcium, that we're actually, and neon once again in these actual remnants. And so I think a natural question to ask is like, well, where does all of this material go, right? Like we know, like, cool, Evan, the material gets ejected, so like what actually happens? And what ends up happening is that these metals live on and they end up getting recycled. You have this interplay between when a star dies, when it enriches its surroundings, and then when it enriches the surroundings, specifically, getting star formation once again. And so it's this big cycle that keeps occurring over and over and over again. In other words, there's no information and no metals that are lost. So another way of actually seeing this, and there's a point to why I'm going over this here. Another way of seeing this is that visually, you start out with some cloud of gas and dust that condenses and makes effectively two different populations of stars, small and large. We're going to just neglect the small stars for now and just kind of look at what happens with the larger stars. Over time, they end up going kabloom, just like we saw schematically earlier. And then that material is then going to get integrated into the next form or into the next population of stars. And then so on and so forth ad infinitum, ad nauseum. So one way that you can probe this very first population or the very first metals from these massive stars is by actually just looking at these smaller stars and trying to observe them. And the reason is because of the different timescales that we're probing between small stars and massive stars. In other words, small stars live for a very, very long time. Depending on the mass, they live longer than 10 billion years. Whereas for the least, whereas for the most massive stars, they end up only living for less than 10 million years for the most massive of them. And so, just to give you an idea of what, because since I feel like I owe it to talk a little bit about the difference between billion and million. So a million seconds is about 10 days. A billion seconds is about 30 years, right? So we're talking about the difference between 10 million and 10 billion. That is what we're talking about. 3 orders of magnitude. So anyways, the idea here is that if you can find some of these oldest stars that have been enriched by these first supernovae, then that gives you an indirect probe for what these metals actually were. And that's what we do. And so there are folks, Alex Shee, who actually gave a talk on this very subject a few months ago for Astro on Tap. He does this, and my collaborators also do this as well. So there is unfortunately an issue, which is that stellar atmospheres are really complicated. I won't dive into the details. All that we really need to know is that, pulling out the metals and trying to observe and derive how much of different metals that you're getting is really difficult to do if you have the complications of a stellar atmosphere. And so even though we get to observe these, what we're called population 2 stars, population 2 stars, the ones that should have condensed from these from the metals from the first stars, from the population 3 stars, their complications depending on the different element that you're trying to observe. So this leads to an interesting question. Well, what else could we possibly do? Evan, you've told me that these stars are that they aren't here anymore, likely because of how short of a time span that they live. So what can we do? One thing that we can do is we can try and actually measure the gas directly. Very interesting. And so we are actually going to invoke another physical law, physics, where we use one of Kirchhoff's laws of spectroscopy. So there are actually 3 of them, but we're just going to focus on this one here, which is this, where you have some light bulb or some emitting source that's passing through a cool gas cloud. And this is the resultant spectrum that we end up getting. So in other words, if you can characterize this, if you have an idea that you're going to be looking through cool gas, then this is what your spectrum is going to be looking like. Admittedly, this is actually kind of true for stars, for stellar atmospheres as well, but there's a complication that rises up that if you're curious, we can talk about it. And so this is what we're trying to look for. And it turns out that in the universe, we actually can. And we try to probe the gas in proto-galaxies to give us an idea of the abundance of metals from the first stars. So our background source, going with this analogy, are quasars. So this is a quasi-stellar radio source. The point with this is that it looks like an actual star, but it's a very massive a galaxy that's accreting at close to the Eddington limit. And again, the point is that it just looks like a star, and it's cool. There's actually a really cool history with Caltech and quasars. If you're ever curious about it, we could do that. Could look through it. The next is that light's going to pass through these proto-galaxies, the exteriors of these, and we call them damp Lyman alpha absorbers, but we can just think about them as DLAs. And the point here is that they're made out of gas, basically. And we will observe this. And so what I want to do really quick is just step through what this would actually look like if we try and observe these. So we're actually riding the wave from a quasar. And if you notice, we have a spectrum at the bottom, and as we're passing through these clumps of gas, you notice that all of these dark areas, or really all of these dips in this light curve, are showing up. And if you notice, the actual spectrum is shifting to the red, or in other words, red, it's being red shifted. And so what we do with this is we take the spectrum and we effectively try and disentangle and find as many absorption features that are related to this one feature. And what we do from there is we actually look at the different metal absorption lines, and that is where our metals are from the first stars. But not yet, though. We unfortunately have to be a little bit more careful than that, because it turns out, as we can just see from here, that although I said earlier that massive stars were the first alchemists, this does not mean that massive stars are the only alchemists. So there are other ways that metals can indeed be formed, and we have to be careful that the systems that we're looking at haven't also been enriched by these other processes, mainly, low mass stars, merging neutron stars, and what have you. So everything that's in blue on the periodic table here are the exploding massive stars. So what can we do to help with that? Well, we add two extra constraints to make sure that we don't get late processes. The first is that we look for metal poor gas, and the second, we look for distant proto-galaxies. So the metal poor part here implies that there haven't been very, very many enriching events that have occurred in this gas's history. In other words, not much has happened. And then distant implies that if something has happened, not enough time in the universe has gone by for the really, really crazy processes like type 1a supernova to occur. And so we end up adding this extra constraint where we now have very metal poor DLAs for our objects. And so we end up now having this edited version where this is what we actually want to see, where we have a metal poor distant galaxy, metal poor distant galaxy, and then a distant quasar that sits out even further, so that we can say, okay, now here are the metals from the first stars. And so as I wrap up here, I think a good question to ask is like, well, Evan, great, what do we actually do with this? And so one of the first uses is trying to back out as much information that we can about the first stars, because unfortunately, again, they aren't here anymore. So admittedly, it's very complicated and difficult to model this because stellar astrophysics. So contrary to popular belief, physicists and astrophysicists really don't like to complicate things because things become unsolvable very, very quickly. So, and that's unfortunately true with the first stars if you want to try and model all their behaviors. So this is one step to help us back out what these first stars actually look like, their behaviors, and what have you. The second and final thing that I wanted to mention is galaxy evolution, and in particular, how do we go from a metal-free reservoir of gas to the metal-rich universe and the metal-rich systems that we enjoy and live in? And so that's the main takeaway. And for what it's worth, this is the best that we got at the moment until we can get that 100-meter diameter dish on the moon, or the 100-meter diameter mirror telescope on the moon. The best that we have currently is trying to probe the gas from metal poor proto-galaxies, as well as trying to measure the abundances from metal poor stars to try and figure out where are the metals from the first stars. All right. Thank you very much, everybody.
Awesome. Thank you, Evan. That was great.
Thank you.
I encourage members of the audience to ask your questions, as people have been doing thus far, which is great. Ask your questions in your YouTube comments or the Facebook Live comments, and I will ask them of Evan. So there's already been a few questions. Let me ask some of them. Here's one from Usman Kazi. Can you give a simple explanation of why helium nuclei collide to form carbon, which is element number 6, where helium takes, has two, right? Two protons in each, instead of them forming element number 4, beryllium. So why does it go straight to carbon instead of beryllium?
Right. So good question. And admittedly, off the top of my head, I cannot give a very satisfying answer. What I can give is that the picture that, of course, that I outlined is very simple, and that there's a lot more details, as I'm sure the person who asked the question can already knows, that in between each of these elements of life, the final stage is basically hydrogen, or the initial stage would be helium, and the final stage would be carbon. There's actually intermediate transitions and intermediate fusion products that end up occurring to basically build up to that. So same thing, even with like hydrogen to helium, you end up getting tritium at some point, deuterium at another point, and everything basically combines. You can also, specifically for hydrogen and helium, the CNO cycle, right? Where anyway, so that'll be my answer. Is that unfortunately I can't give a satisfying one off the top of the head, but there's basically intermediate processes that make it more favorable to form carbon instead of, beryllium, for instance.
Yeah, I'm trying to think. Off the top of my head, I don't know either. I just assume that with lithium, beryllium, and boron, they have like tighter binding energies, and so it's harder to produce those. But I don't know. That's a really good job. You stumped us. That was a great question.
Yeah, fantastic.
I'll poke around and try and figure out the answer, and then in the next bit while Rebecca's giving her talk. Let's see.
Same.
Other questions. What kinds of pressures are reached at the peak before the rebound begins? I think this was in relation. This is Chris Georgi. Perhaps I may be messing, or Georgie, I may be messing up the pronunciation. Forgive me, sir. But during the supernova, when you've got the collapse of the core, what kind of pressures are actually achieved before it starts blowing out into, like, the Crab Nebula, which you showed was a supernova remnant?
Right, absolutely.
Super question.
Yeah, once again, indeed, these are fantastic questions. So if my stellar astro course serves me well, I think the number is somewhere upwards of, Evan is gonna be livid if I can't remember this off the top of my head. It should be upwards of 10. So I'm gonna give this number in dynes per centimeter second. So this is the CGS units for, I imagine this person is in the know. So this is centimeter grams per second, or centimeter gram second. It should be upwards of 10 to the 17. So for those that are unfamiliar with how big of a number that is, take 1 and then put 17 zeros after that, and that would be, if I'm remembering correctly, the pressure. So that actually wouldn't be the pressure right before or during core collapse. That would just be what you would need to get to I think it's to the final stages of silicon burning, where you're actually fusing silicon to nickel 56, or okay, technically to silicon to iron. And so that would basically be like a lower limit, right? So it would have to be upwards of 10 to the 17, if I'm remembering correctly. Yeah. Once again, very, very good questions. But
Yeah.
I mean, yeah, so the takeaway is that the pressures are just insane, just ridiculous, right? Nothing, nowhere else would be able to get these pressures in the universe. So impressive nonetheless.
Indeed. It's crazy to think about pressures that exceed what we can produce in a nuclear reactor or even in the interior of the sun. You know, it's just outrageous.
Insane.
Let's see. More questions. Here's a question from Julia Miguel Bernardis. Can we go over once again about the difference of what metals are in physics versus what metals are in astronomy?
Yeah, absolutely. So metals in astronomy.
For people, we get so accustomed to talking about metals in astronomy, and then people are like, wait, oxygen is a metal? Wait.
Right.
Carbon's a metal? Yeah, you're like, oh, wait.
Absolutely, yeah. So the physical definition of a metal, first off, is actually physical, right? Like it has to have a certain gosh, I'm already blanking on it a little bit, but there are certain properties in terms of like how conductive the material is, you know, and then that is related to specifically how free electrons are to flow across the surface and what have you. Its resistivity and stuff, all that good stuff. So it's actually like grounded in actual physical experiments that you could see like, oh yeah, this is absolutely an actual metal compared to, you know, oxygen and what have you. For astronomy, since there are so few metals compared to the amount of hydrogen and helium, it's just simpler for us just to be like, yeah, it's all metals. So for what it's worth, I don't want to say we were lazy about it, but since it's such a small fraction, yeah, we're kind of lazy about it. And of course, you know, there are actually astrochemists that this really does make a big difference. And of course, you know, what we call as metals do indeed behave differently. So for instance, in the interstellar medium, there's a lot of fantastic astrochemistry that goes on that even though we would call, you know, polycyclic aero hydrocarbons a metal, as well as the gaseous oxygen a metal, they act and behave very, very, very differently. So this is more of a statement of terminology and phenomenology, much more so than anything rooted in actual physics. So yeah, if anything, this is good to know when we're talking about, much more so than like applying anything physical to it. So hopefully that makes a little bit more sense.
Yeah, I think that's a good explanation. We'll take a couple more questions before moving on to our next talk. Here's one from AG. Hydrogen is the simplest element, so we can see it created at the beginning of the universe. But how did helium form right away as well?
Right. So that's first off, good question. And there are a few different channels for how we know or how heavier elements get synthesized. The first is in the cores of massive stars. So this is what we call hydrostatic burning. So this is basically what the sun is doing right now. It's fusing hydrogen to helium. The second is what we call explosive burning, and so this is when you have the explosion of a star. And the third is what we call Big Bang nucleosynthesis. So, in other words, at the very, very beginning of the universe, when everything began, the temperatures and the densities were favorable enough that we were able to get hydrogen to fuse into helium in pretty significant abundance compared to the rest of the metals. And so that's the short answer, is that basically from the actual Big Bang itself and from the conditions gosh, I lost it.
Well, just the early universe, really. I mean, it was
In the
just
conditions of the early universe. There you go.
super dense, and so it was much in those first few minutes of just after the Big Bang. It was really similar in some ways to the cores of stars, where it was super dense, high pressure, and the conditions where these nuclei could, you know, protons could slam together and form helium nuclei, and not just hydrogen nuclei. But it quickly kind of expanded and the pressures dropped and the densities dropped, so it wasn't able to do any additional heavier elements beyond helium. But yeah, I mean, exactly what Evan talked about in his presentation. So
absolutely. And again, and within that framework too, you were able to get very, very, very small trace amounts of lithium as well. And again, this was for an even shorter amount of time because again, for the temperatures and the densities to make that occur even more difficult compared to getting hydrogen to fuse it to helium. So yeah, really good question. Once again.
While this is expanding and cooling and getting lower density. So yeah, it's like,
Mm-hmm.
all right, there's only a little helium and lithium form.
Mm-hmm.
Okay, one last question, and that is, why were the first stars so large? Why were these population 3 stars? Why do we think they were so much larger than the ones that are around now?
Absolutely. So great question. The answer that's always felt the most satisfying to me is the fact that since there were no metals, you didn't really have an engine to keep the star from growing effectively and from from losing mass. So in the most massive stars that we notice in the universe, they actually go through really significant phases of mass loss. And the reason this occurs is because you have heavy elements in the envelopes of the massive stars itself. Whereas for the first metal-free stars, this just doesn't. They just don't have this. And so the idea here is that seemingly you'd be able to get incredibly massive stars as a result of the that process not being there. Yeah,
that's absolutely right. Okay, great. There are more questions and they're really good and I want to ask them, but we've also got to keep moving. So I appreciate everybody's questions. Maybe we'll revisit some of this stuff during the pub trivia at the end. So maybe that we'll be able to try and address some of these questions, but excellent questions. Evan, wonderful presentation. Thank you. And we will move on to our next speaker. Rebecca, do you want to join us?
Sure.
Hello.
Hello.
How's it going?
Good. I miss you. I wish I was in Pasadena.
Yeah, I know. So everybody, Rebecca is in charge of Astronomy on Tap for Austin, Texas, which is, I think, one of the largest Astronomy on Taps ever. You guys have, in your in-person events, have like 300 people who show up. They're like stadia that are,
yeah, it's a whole production. And we were very lucky to have an amazing venue that could fit that many people with a 2-story screen and a stage and a bar and lighting and all it's a big event space. And quarantine, we can't really do anything in person, and so we were doing a lot of our online shows. We're taking a break right now, but we will be back soon. If anybody is interested, we also have a YouTube channel, just like Astronomy on Tap here in LA, and all the Caltech Astro Outreach stuff that Cameron is leading is amazing. If you want even more astronomy and more space, by all means, I think the link to our show is also in the video description.
It's in the video description, and it's also in our featured channels. I think you are one of our.
Wow. We follow each other officially.
You guys have great content and great events.
Yeah.
So check it out.
Thanks.
All right. Okay. Here's my formal introduction for you. So Rebecca Larson is a PhD student at the University of Texas at Austin. She's a U.S. Air Force veteran and the host of Astronomy on Tap, Austin, Texas. She studies galaxies at the beginning of the universe, ones that existed 13 billion years ago, to learn how those galaxies and the universe itself evolved into the one that we live in today. He also speaks Arabic near fluently. It's true.
Just gotta call me out like that.
Yeah, well,
it's been many years since I've used it, so I wouldn't say I'm fluent much anymore. But yes, that was what I did in the military. So I was officially trained as an Arabic translator.
Yeah, that's awesome.
Yeah, slightly different job than what I do now, but
Well,
somebody mentioned earlier in the chat that like they're gonna go do astronomy when they retire. And I just wanted to give like a very quick, I know I'm supposed to be talking about science, but it's never ever too late to do something that you really love. I think Cameron and I can both attest to the fact that you don't have to do this like straight out of high school and pick a degree and then stick with that and do that career. It is incredibly difficult, but it's very important to change careers if that's something that you really want to do. And I fell absolutely in love with astronomy, and I got here by accident. So I would encourage you that if it is something that you're very passionate about, that definitely never too late to start.
Lots of trajectories, and everyone gets obsessed with the standard, like I went to high school, I went to college, I went to graduate school, I became a professor. And that is not what a lot of us do. So
no.
If you're interested in pursuing this at whatever level you want to, if that means going to graduate school and doing science, or if that means like hanging out and drinking beer and talking about science, follow whatever paths you desire.
I switched to whiskey for you.
Whoa. Well, I've got to step up my game.
Yeah, I do. I don't have a drinking game though, so I was smart enough to wait and drink my coffee during the drinking game. So maybe I'll be coherent this time.
All right, I will let you take it away.
Sure. Awesome. So thank you, Cameron. Thank you for having me. It's always nice to get to do a different Astronomy on Tap because I don't usually get to give talks at my Astronomy on Tap. I do the thing that Cameron does. So I host our show in Austin here. But tonight I am going to be talking to you about the science that I do. So what is my day job? And I cannot get the Zoom window out of my way. So that's super fun. Gosh, you'd think at this point we'd be pretty good at this.
We can't.
I know, but I can't see. It's oh, okay, whatever. All right. So like Cameron said, I'm a PhD student and a National Science Foundation Fellow, host of Astronomy on Tap ATX. And I am talking about searching for galaxies at the beginning of the universe, both from Earth and from space. And so to do these things, I want to talk a little bit about what does that mean by galaxies at the beginning of the universe. Evan gave an amazing talk about some of the first stars. So you're going to hear a lot about the very early universe in this particular show. And so it kind of worked out that we were doing these two talks together. And so here I'm showing a little pictograph, basically, of cosmic history. And so if you're looking on the left is the Big Bang, the beginning of the universe. And on the right of this is, I don't know if my camera is that way, but on the right of this is today. And so this is showing time increasing, going towards the right. And I will talk about something called redshift, which is a way that astronomers use to indicate how far away something is, but also how far back in time something is. And so redshift actually today is redshift 0. And so back into the early universe, redshift increases in number. And so the higher the redshift, the more distant the galaxy is and the longer ago that it existed. And so when you hear me talk about those things, that's what I mean. So Evan was talking about some of the first stars. And so you can actually see the Big Bang and then the release of the cosmic microwave background here on the left. And then you see all this kind of yellow, we can't really see through, it's very opaque. And then you see some of the first stars, they start to make little pockets where you can start to see them. And then these bubbles get bigger as we get galaxies to start to build. And then at the end, you have a bunch of stuff that you can see through and you can see all the galaxies. And so in this particular picture, all this yellow here is neutral hydrogen. And it is opaque to ultraviolet radiation or to bright stars or to most of the light that we see from galaxies in the early universe and even from some of those very early stars. So we need to actually ionize that hydrogen. We need to break apart that proton and electron and for the light to actually travel through it. And so this process is called reionization, where the stuff in between galaxies went from being neutral hydrogen to ionized hydrogen. And around the ionized hydrogen pockets are these ones that you can actually see through and see these first stars and these first galaxies. And so not only are we looking for the objects that we're looking for, but we have to look through all of the universe to do those things. And so we talked about line of sight in the previous talk, and this is kind of a similar concept to where you need to be able to see through kind of the fog of things in between galaxies. And so this is a little bit of a diagram to explain redshift. Why is it called redshift? Astronomers are super great at naming things, just like metals being anything not hydrogen and helium sounded like a good idea to us at the beginning, and maybe not so much today. But redshift is just because the light is shifted to a redder wavelength. And that is due to the expansion of the universe. And so here at the top, you can see that if a galaxy emits blue light, it is emitted at a blue wavelength, so a shorter wavelength. And then as it travels from that galaxy to us, it is traveling through a universe that's expanding. And so that light is actually getting stretched out as it passes from that galaxy to the Earth. And so over time, if you have a galaxy that's quite far away, it's going to stretch out during that whole time as the light travels to you. And so the more distant something is, the longer the wavelengths are stretched out to. And red light has longer wavelengths than blue light. So things that are far away from you that shift into longer wavelengths are called redshifted. And those are the ones that are moving away from you and being stretched as the universe is expanding. And things that are blue shifted are things that are coming towards you. Because again, astronomers are brilliant at naming things. And so you'll see here on the right a little graphic showing two different galaxies emitting light, but at different times. And so this galaxy here in the bottom, its light reaches us at like a green wavelength, whereas the one at the top left earlier, and the universe is expanding at the same rate. And so it ends up being stretched into the red. And so the amount that the light is redshifted actually tells us a lot about how far away that galaxy is and how much it has stretched over time. And so this is a fun little movie that was put together to kind of explain what this looks like to us as we're looking at our data and how we determine the distance to an object or measure the redshift. And so here I'm showing at the bottom a bunch of little pictures of this galaxy that were taken with different filters on the Hubble Space Telescope. And at the top is a graph as a function of wavelength. So you have bluer wavelengths on the left and redder wavelengths on the right. You have this gray shape basically, and that is the amount of light emitted by this galaxy. And you'll see all these little colored graphs, and those are going to be the filters. So these are the wavelengths that these particular filters cover, and they correspond to the picture below it. And so as the galaxy is as redshifted, as we simulate a galaxy that is at further and further distances to us, you'll see that this gray shape is actually getting dimmer because it's getting further away, but it's also dropping out of certain filters as that light gets stretched into redder and redder wavelengths. And so what you see is that this galaxy starts to not show up in these shorter wavelength pictures and only show up in these longer wavelength pictures. And so the point at which we stop seeing this galaxy or start seeing it, depending on which way you want to look at it, is how we determine the redshift of this galaxy. And so what we end up seeing is the galaxies are emitting this blue light, or ultraviolet light is actually what I'm looking for. And the further and further and further away it is, the longer it gets stretched out, and it gets stretched out into infrared wavelengths. And so if you're familiar with the electromagnetic spectrum, this is kind of what it looks like, where visible light is the light that your eyes can see, where infrared light is a little bit longer, which microwave and radio are even longer than that. And then ultraviolet is shorter, with X-ray and gamma ray being the shorter ones. And so it's nice that visible light is what we see in, because that is the light that reaches the ground. And all of our galaxies are going to emit light at all wavelengths, so to speak. But the ones that we're looking for are these big, bright galaxies early on in the universe that emit a lot of ultraviolet radiation from these big, bright stars, kind of like the ones that Evan was talking about. And now that ultraviolet light is actually getting stretched into the infrared, because that's how far away these galaxies are and how long it took the light to get to us. Over 13 billion years of the universe expanding stretches those wavelengths into the infrared. And at the bottom here, you'll see this kind of gold. And this is how much of the light of those wavelengths is blocked by the atmosphere. And now the atmosphere is great because it allows us to, breathe and live. But at the same time, it's kind of a pain because it actually blocks a lot of the light from space, which again is good because harmful radiation, all those other things, the living is nice. But for science, it's kind of difficult if what I want to do is I want to look at the infrared. I'm not entirely sure if you can see my mouse, but here is infrared wavelengths. And this is the atmosphere blocking a majority of those wavelengths of light. And so we're not getting them from the ground very easily. Whereas visible light, you can see from the ground, and radio as well. And so we can actually study galaxies with radio. And I won't really focus on that because that's not my expertise. And we can do that from the ground with things like the ALMA telescope array and things like the ones that you've seen in Contact or some of those other big radio dishes and arrays of radio dishes. And so we can do that from the ground pretty easily, as well as visible light astronomy. But infrared is kind of difficult, as well as some of these other wavelengths. And so it doesn't mean we can't do it. We've built lots of telescopes on the ground, in fact. And so here is a really cool little graphic showing different sizes of telescopes. Now, if you want to study a very faint thing, you're going to need to collect as much light as you can from that object. And for galaxies that are very, very far away and existed a long time ago, they're quite faint. Just like if you had a flashlight and you started to walk away from somebody, that light is going to get fainter and fainter and fainter to them the further away you get. This is the same thing that happens when we look at things in space. The further away they are, the fainter they are, just because of the nature of how the light intensity isn't increasing over time, it's decreasing as it gets further away. And so to see faint things, you need bigger telescopes. And so we have built lots of telescopes on the ground. Here are a few of them. I will give a bit of a shout out to a few of my favorites, and I'm mostly biased because, well, I've gotten to use them. And so here we have the Hobby Eberly telescope. This is a telescope owned by the University of Texas at Austin. It's out in West Texas. You can see it's got a bunch of different little mirrors that all work together. They actually kind of all move separately and individually, and it's a really, really cool telescope. We also have the Keck telescope, which is a set of twin telescopes who also have segmented mirrors. This hole in the middle is where all the cameras and instruments kind of go to. And so the light kind of comes through and you can actually send it to your instruments to take pictures. You'll see that hole pretty much in a lot of these styles. And you'll also want to, like, while you're here, look into this picture. This is the Hubble Space Telescope mirror size, and these are all to scale. Right? And then these are things like the Giant Magellan Telescope, which is currently being built in Chile. This is going to be much larger than a lot of these other ones. And, you know, of course, these are some of the planned big 30-meter class telescopes, because more light, even better. And then I will also point out here that this is the James Webb Space Telescope mirror size, which I have my own drinking game whenever that gets mentioned. And I can come back to this if we want to clarify that. But basically, you want a big telescope to gather as much light as you can from a faint thing. And in fact, there's another aspect to this, and that is if the wavelength of light is longer, your resolution depends on how big your light wavelength is relative to the size of your mirror. And so in longer wavelength astronomy, such as infrared astronomy, you need a bigger telescope in order to get a higher resolution image, because you need to get the corresponding size between wavelength and mirror size to be ideal for you. And so for what I'm trying to do, looking for distant things that are in the infrared, it is ideal that we have a bigger telescope. And so this is a really cool picture of the top of one of the volcanoes in Hawaii, where it's the dormant one. This one doesn't blow up. Okay, so we put telescopes on top of here, and it's really nice because it has, it's very dry. We are very high elevation. We're above a lot of the clouds. You can kind of see at the bottom of this picture, the clouds are below these telescopes here. And then off to the right, like I mentioned before, are the twin Keck telescopes. You can see the little laser coming off of one of them. And I've been very fortunate to spend the past few years using these telescopes to look for distant galaxies. So here's another picture of them. Again, I will be biased. There are plenty of things you can do in astronomy that are not specifically what I'm talking about, but I am definitely going to focus on things that I know better. So the Keck Observatory is responsible for some record-breaking galaxies. And that just means we found the most distant galaxy with this telescope several times now. I mean, records are meant to be broken, right? So you found the most distant galaxy in 2013 was found by my actual boss, Steve Finkelstein, using the Keck Observatory telescope. And we're doing this looking for very specific bright signatures of star formation in these galaxies. Right now, though, the current ground-based record is been broken. And so we're showing here a picture of the galaxy from 2013 that my boss found. And you'll see that it's a little bit red. And that's also because that light was shifted into redder wavelengths. And so it's going to appear to us in this image, which is from Hubble, that it's going to be a little bit red. And so it's pretty cool that we're able to do this from the ground. This galaxy existed 700 million years after the Big Bang. So in the first billion years of the universe, universe's history. The universe is 13.8 billion years old. And so the stuff that we're studying and trying to understand happened in that first billion years. And so we're able to do this with some of the biggest telescopes on Earth with a lot of time and a lot of effort. But we could probably use space telescopes and not have to deal with the atmosphere. And so in fact, again, we're showing kind of the redshift situation here where redshift is increasing to the right. This is now reversed. And I don't know how to reverse images, or I would have kept everything kind of consistently in the right direction, where today is now on the left and the early universe is now on the right. So redshift is increasing to the right this way, and time is increasing to the left. And so you can kind of see the correspondence of like redshift 7 being 800 million years after the Big Bang, whereas redshift 4 is 1.5 billion years. And it's not a linear correlation, because that would make way too much sense. Okay, so ground-based telescopes have been able to probe back into like halfway through the universe's history. And with some of the new telescopes that have infrared instruments, we're pushing back to like this general range. This graphic is a little bit old. And so with Hubble, we're able to look further back. And that's partially because we are getting the atmosphere out of the way, because the Hubble Space Telescope is in space, and we have instruments on it that work in the infrared. And if we spend a lot of time staring at a specific spot in space, we collect a lot more light, right? And so some of these deep fields where we spend a lot of time looking at them, we're pushing further back into the universe's history here. And future telescopes are going to even be able to go further and further back. There's like a whole other thing. So let's talk about Hubble. So Hubble was launched in 1990. It's very cute. You can see a very good picture of it here. It orbits the Earth, and so it kind of goes around the Earth every, I want to say close like an hour-ish to go around. Since it orbits about 40 minutes of data, I believe. And so the actual mirror size, this telescope itself, the whole thing is about the size of a bus. So kind of for reference for you, that's how big this thing is in space. And the mirror inside of it is 2.4 meters. And so this is actually an amazing telescope, and I don't want to knock it because I love Hubble. Hubble has honestly changed the face of astronomy. It's inspired millions of people. Most of those really pretty pictures of space, even some of the ones that Evan showed, were pictures that were taken by the Hubble Space Telescope. And it's allowed us to really study more of astronomy and more of the universe than I think we ever really fully expected when it was launched. And so it is responsible for the most distant galaxy currently known. This galaxy has a great name of GNZ11. It is in Goods North, which is where the GN comes from, and Goods is actually another acronym because nested acronyms are cool in astronomy. And it's called GNZ11 because it's at Z, or redshift 11. All right, so now that we've gotten that embarrassment out of the way, we can talk a little bit about, this was the current ground-based distance holder here. So again, today is on the left and the Big Bang is on the right. We're now in the same orientation as before. And so our ground-based telescopes were able to push back into the history of the universe at about 13 billion years ago. And then this is about 13.5 billion years ago that we're able to do with Hubble. And we actually were able to use gravitational lensing to assist in this. So a big bright object was in between us and this galaxy, and it lensed or brightened this particular galaxy enough that we were able to see it with Hubble. So this is really cool, right? Like we're getting further and further back in the universe's history. We're finding these galaxies. We're trying to like understand more about them. We got to find them first. And so this is this whole process and this whole search for these distant galaxies. But we want to go further back. And Hubble is also quite small. And we also need a big telescope to do infrared wavelengths, right? For a higher resolution. We also need to be in space. So we're going to, knock on all of the wood, launch the James Webb Space Telescope this year? Question mark. Hopefully. It's scheduled to launch in October. And this particular telescope is the size of a tennis court. And so this image that I'm showing you here is actually a mock-up fake telescope, but it's really full scale. And so you kind of got to see the whole telescope life size, and they brought it to South by Southwest, which is this cool music festival here in Austin. And so one of my favorite pictures is this life size telescope with people at the bottom for scale, with my city skyline that looks incredibly different now in the background. This particular telescope isn't going to orbit the Earth like Hubble did. It's actually going to orbit L2, which is a stable gravitational point past the moon. So this telescope is going to be 1,000,000 miles further away than the moon, and it's expected to work for over 5 years. It's really pretty because it's got a segmented mirror that's actually gold plated, and that's not just because it's shiny, that's because it actually is more reflective in infrared light. This whole shield here is going to protect the telescope instruments from heat of space and the sun and the Earth and the moon, and it's a really cool engineering feat, and it's basically a giant transformer. This telescope is the size of a tennis court. You cannot fit a tennis court in the rocket just as it is. So what they decided to do was, let's just fold it up and then put it in the rocket, and then we'll launch the rocket into space, and then we're going to unfold the telescope in space as it travels 1,000,000 miles past the moon, all fully automated on its own, and everything's going to work great. Not at all stressful. Anyway, this telescope is going to be amazing because if you think about some of the things that Hubble taught us about the universe, if you've ever seen this image before, this is the Hubble Ultra Deep Field, meaning Hubble stared at this tiny little spot in the sky. And here at the bottom on the right-hand side, there's the moon for scale, which I hope you're familiar with. And then on the bottom, there's a little square. This is the amount of space that Hubble looked at for a lot of hours, and we found 10,000 galaxies in this one tiny little spot of the sky. And we're able to study so much with Hubble, and it's going to be amazing. You'll see that almost every single spot of light in this image here on the left is a galaxy. They're different sizes, they're different shapes, they're different colors, they're different distances. And this helped us understand a lot about the universe, how it evolved into the one we live in today, because you can see galaxies from different times in the universe's history. And so if we wanted to simulate what JWST, James Webb Space Telescope, is going to see, it would look something like this. And this would be the same amount of area that we'd be looking at on the sky, but you would see even more galaxies because you're sensitive to a lot more. You have a much bigger telescope mirror. You're also going to see different types of galaxies because you're looking at different types of wavelengths of light, because this one is going to be an infrared telescope, where Hubble was predominantly ultraviolet and visible light. And so not only are we going to be able to study further galaxies, but we're going to be able to study even closer galaxies in more detail, and we're going to be able to study different parts of them because we're going to be looking at different wavelengths of light. And this telescope is going to be very, very, very exciting. And so we also have more telescopes that we're building in the process of making happen, and those are also going to kind of change the game. And so the Roman Space Telescope, named after Nancy Grace Roman, is another space telescope that's going to be launched, and it's also going to be working in the infrared. And if you take a look at that little square in the center of this image, that is the field of view that Hubble and JWST can see. In one, like the one image they take is this big. But the Roman Space Telescope, this blue square, which is a weird shape, but you know, this blue square, this is one image with the Roman Space Telescope. So now we're going to be able to study even more of the universe at one time, because if you wanted to study big parts of the universe, you're going to have to take a picture and take a picture and take a picture with the other ones. And if you need to do a lot of exposure time to get fainter things, it costs a lot more because you're covering less area at one image. And so the Roman Space Telescope is going to do amazing things by covering a lot of area all at once. Now, it's not just space-based telescopes that we're building. They're really cool. I mentioned the Giant Magellan Telescope earlier. That's that one with those big, big mirrors that they're building right now in Chile. And if you take a look on the left here, this is kind of a theoretical model of the universe where time is increasing from left to right. And then in the Y direction, or the up and down direction, it's a spatial cutout of the universe, so to speak. And so this little square here at the bottom that says JWST, that's that field of view that Hubble and JWST can see. The Keck instrument that I've been using in Hawaii can see, it's got a bigger field of view when it looks at space, and so it can see more of the universe at once. But this big, big circle right here, this is what the Giant Magellan Telescope, or GMT, is going to be able to look at one time. And so there's a lot of things that we're building right now that are going to help us not only do this from space, not only look further back in time, but also cover more of the universe, so we get a better understanding of the big picture of not just one galaxy, but let's study several of them at once. And GMT is going to be from the ground, so yes, the atmosphere is going to be a problem, but it's going to have really cool lasers. And so those are going to actually measure a lot of the atmosphere. So you'll be able to delete it out of your data when the time comes to actually look into science with them. And so I will leave you with this really cool video of the James Webb Space Telescope unfolding itself in space. This is not a real video, mind you. This is the actual like animated version of what's going to happen when this launches. And I will let that play for a bit and I will take questions.
Awesome.
And I will drink a lot because this stresses me out.
That's awesome.
But you guys, it's a giant space transformer. Do you see this thing? This thing is all folded up and it's going to unfold and look like that thing in the other picture.
How long does it take?
It's about 30 days for it to get from, when it launches to where it's going. At the bottom, you'll actually see it showing where it is relative to the Earth and the Moon at each one of these stages. Yeah, we don't have to, we can talk over this if you want. This link to this video is also in the YouTube description. So if you would like to take a more detailed look at this, then you can definitely find that there and stress about it as much as I am.
Well, hopefully it'll stick to the timeline now and we'll have a telescope in space in less than a year.
Yeah. Oh man. So excited.
So you and Steve have, I saw with, so everybody, when you want to use an instrument like the Hubble Space Telescope or the James Webb Space Telescope, there's a proposal period where you submit proposals. I want to do this cool science with this instrument. Let me do this cool science. I'll tell you this and this and this if you give me 5 hours of observing or 2 hours of observing or something like this. But I saw on the first announcement that you and Steve, your advisor, got time on a couple of proposals, right? To use the James Webb Space Telescope, right?
Yeah. I am incredibly fortunate and very excited to be part of several teams who are getting some of the first data to come back from this telescope. So we're part of a program that was awarded time by being involved in the making of the telescope. And my advisor also led an early release science program, which was meant to be a test case to test the telescope capability once it was launched, make all the data public, and give a bunch of data to the community really early on. And so we're leading that particular project. And then in November of last year was the first official call that actually went through for proposals to use the telescope just to general observing time. And my advisor led a proposal that also got time through that program to do a deep field, almost like the one that Hubble did. So to start working on building up a deep field with the James Webb Space Telescope. And among some other projects that were also involved in that got time. And so I feel very lucky and I'm very excited and I am very, very stressed that this actually happens because I really, really, really want to see some of the science that we're able to do with this incredible telescope.
So this baffle at the bottom is a sun shield, is that correct?
Oh yeah. So there's several different layers of it. So basically, you can see at the bottom that the Earth is here and the Moon is here, and the sun will be, even further off the screen to the left. And this telescope is going all the way out past the Moon, and this shield is going to always be between the telescope and us, because infrared is also heat. So if you've ever seen like night vision goggles where you can see heat, or like you can see people radiate their heat, that's infrared wavelengths of light. And so the Earth is warm, the sun is definitely warm, the Moon is warm relative to space, which is very cold. And so we want to block out a lot of that infrared or heat from the rest of us and the sun from this telescope, so that the telescope is able to detect the things in space that we're trying to find without that kind of interference. And so that's what this big layer of material is to block out all of that radiation from reaching the telescope nearer. And then behind the telescope are all the instruments. And so it's also going to keep those cold too.
That's awesome.
Yeah.
Okay, we have questions from our audience here.
Cool.
Lots of questions. I'll try and pick out a handful before we move on to pub trivia. But let's see. A question from our Facebook audience. Alias Alma asks, hypothetical question, were the universe to start shrinking, would we still be getting redshift from more distant galaxies? Seems to be it would be, you'd start getting blue.
You would get redshift still because they're still far away from you, right? So like they're already starting at a redshifted position. Now, I would assume in this hypothetical situation, the whole universe starts shrinking all at once, in which case things would start to blue shift as everything started to kind of come towards you. Since you're already starting at a redshifted position, you'd still see redshifted galaxies. They'd just be less redshifted. And also that math would be really complicated.
Maybe they'd start to cancel out the redshift from,
But although, to be fair, it's taken 13 billion years for it to redshift this far. So we would have to kind of shrink the universe for a very long time for us to cancel out the redshift that's already happened. And that math sounds really complicated. So let's not do that.
Let's see. Another question. What objects apart from galaxies, this is from Suhail Valle, again, forgive my horrible pronunciation, guys. What objects apart from galaxies can you observe at redshifts greater than redshift 2?
Honestly, there isn't anything. So right now, when we study stars and planets and things like that, we're studying the ones that are in our own galaxy. When you start to get to maybe Andromeda, which is still right here, redshift 2 is 6 billion years ago. And at that point, all of those objects are pretty small on the sky. And so you don't really have high enough resolution to study individual objects in them. Oftentimes you can study like maybe here's the gas or here's some pocket of star formation. But as far as like individual objects in these distant galaxies, you're not going to be able to really make those out, especially things that are, that far away.
Except quasars.
Quasars are galaxies.
Quasars are the cores of galaxies.
Quasars are the noisy black holes at the middle of these distant galaxies that are very bright, such that they're kind of brighter than the rest of the galaxy itself. And so I would argue that you're getting the whole galaxy in that quasar. It's just the black hole's louder and brighter.
Yeah, I don't know what the limits are on the highest redshift supernova that we have. I don't think they go above redshift of 2.
I don't believe so.
Maybe if it's lensed, you can get above redshift of 2. I'm not sure.
Yeah.
But yeah. And gamma ray bursts, we do see them at cosmological distances, but again, I don't think they go above redshift 2.
When I talk about like high redshift, I'm very, very, redshift 0.1 is technically high redshift. It is outside the local universe. It is time has progressed. And like we showed at the bottom of one of these pictures was like redshift 1 is half the age of the universe. And they kind of become smaller increments of time later on because it's not a linear thing. So redshift 1 is, 6 billion years ago. And so you're covering a lot of time, even at redshift 0.1 and all these other things. And so I would just, when I say like redshift 7, 8 and all these things, it seems like not that high, but keep in mind that the gaps are not the same in redshift space as they are in time.
That's true. Yeah, I sent a figure showing the relationship between redshift and distance and time, and show how crazy nonlinear it is to the YouTube chat. I'm sorry, the Facebook. I'll post it in the Facebook.
Cool.
As well.
Thanks. Yeah, it's not exactly direct.
Weird. Yeah, people are like, wait, so.
It's one of those things where it's kind of like, you go half and then you go half again and then you go half. It's kind of that concept. Yeah.
Here is a great question from Ashley Landquist. These older galaxies don't look like elliptical or spiral. Are older ones less likely to take those shapes for some reason?
Yeah, it's actually a really good question. So when I talk about how do we understand galaxies from the early universe and how they evolved into the ones we live in, I also mean how do galaxies evolve over time? So in today's world and in our galaxy, it's a spiral galaxy. If you've ever seen a picture of the Milky Way. And we have galaxies that are spirals and ellipticals and things that have taken a lot of time to kind of calm down to form this structure and be in a stable kind of situation like a spiral elliptical. And typically these galaxies are much bigger because over time galaxies merge into each other. And so throughout the history of the universe, you've had galaxies running into other galaxies and then becoming gravitationally attracted, all that gas and all those stars get all mixed up. And in fact, the way you build elliptical galaxies is you take a bunch of galaxies and run them into each other, and then they all start to just kind of form this ball of stars, and they eat up all the gas to make all of those stars. And they're much older galaxies than some of the younger ones that are the spirals that are still forming stars. And so early on in the universe, galaxies didn't have this kind of structure like these spirals and these ellipticals. I'm gonna stop the screen share. Right, so they didn't have this kind of structure. They hadn't had time to really to build into that movement and that motion. And so they do look different, actually. You know, you are seeing kind of like a little mess of gas and dust and stars, and that's our galaxies earlier on. Those galaxies will then merge into these bigger ones like spirals and ellipticals that we see. So they are fundamentally, physically different types of galaxies early on in the universe than the ones that we see now. You know, we might have built spiral galaxies early on. We might have built elliptical galaxies early on. I mean, defining early is kind of up to you at this point as to what you consider early or late. But yeah, predominantly the ones that I will be studying aren't going to be fully formed into these massive spirals and ellipticals.
Okay, last question before we get to the pub trivia. Stephen Shearer, I'm just going to mess up everybody's. Sorry, Stephen. How soon will the James Webb Space Telescope begin capturing images after it arrives in orbit? So we just saw this whole movie about its unfolding and everything. How long is it going to take till it actually starts taking data?
So that launch to where it's fully where it's supposed to be in the end, and it's unfolded and open and everything, is going to be about a month of time. And then the first data will be about 5 to 6 months after launch, because you're going to take a lot of calibrations. We're going to slowly turn everything on and make sure that it functions, do a lot of tests and those kinds of things before we fully open up the telescope to do its full science capabilities. And so it'll be 5 or so months after it reaches its final destination before the first science data is taken, since we need to take a lot of calibration data beforehand.
So if everything goes according to plan, 1 year from now, nominally, we should start getting those first data.
Yeah.
Okay, sweet.
Mm-hmm.
Sweet.
Yes.
Okay.
So some of our observations are scheduled for like June. And so we'll see.
Fingers crossed.
Yep.
Evan, you want to join us? We're going to do the pub trivia part now.
What happens if we get them wrong?
That's okay. I always sound like Alex Trebek. You know, I'm so like, oh, I've got it all figured out because I wrote the damn question. So of course
you already know the answer.
Yeah.
Okay.
So I mean, Alex Trebek, everybody thinks he's a super genius, or thinks he was a super genius, but who knows? He wrote the questions, or he just had the cards. Who knows?
The answers are right there in front of him. I can win any test that I take that way.
Yeah, I was about to say.
Right there. So, okay, let's see. I will. So everyone should be able to go to, technical difficulties here. Jeez. So we do this, our pub trivia, through something called mentimeter.com. Can you guys see my slide here? This big Astronomy on Tap logo. Yes. All right. So if you are watching this at home, go ahead and open up your phone or another browser or something like that and go to this www.menti.com and type in this little code, 8506-5918. And that will bring up in your other browser window. Heck, I'm going to open one too on my phone so I can answer. I can put in false answers into the whole business and throw everybody off. So this is a way that you can participate, and we will see your responses, and you will see your responses on the screen to each of these questions. 8506-5918. And it's all good fun. Yeah, unfortunately, we don't have prizes, but yeah.
We'll applaud you if you win.
The prize is knowledge.
The gift that keeps on giving.
All right, so first question
cool.
is...
Hey, this is cool.
Yeah, it is cool, right? Last weekend, NASA successfully conducted a helicopter flight test on Mars. How far did it go? How far did it actually travel? So there's 4 different options here. Whoa, people are answering. People are getting going.
So this is not the first test.
This is last weekend. So it was kind of a trick question. You caught me there because I said last weekend. So
right.
The third flight was yesterday.
Right. So we're talking about the second flight?
No, the third flight. Last weekend. Yesterday.
Okay. Dude, I don't know what day it is. I was observing the past few days. So the fact that I'm awake right now is an achievement.
So people are, we're all over the place here, but some good questions. This is super exciting. This is the Ingenuity helicopter.
Guys, there's a helicopter on Mars.
The helicopter on
Incredible.
Mars. It's this little 4-pound drone with double rotors that spin in opposite directions because of course the atmosphere on Mars is like super low density. So it needs to spin higher because it doesn't get as much lift or thrust from the rotors. All right, so we're seeing, looks like either just up and down or 50 meters to the side and back are the preferred ones. And the answer is actually 50 meters to the side and back. And like I said, this is kind of a trick question. So the first, let this thing play.
Oh, you have the video?
This is video from it. So you can see the little dude here. This is taken by the rover looking at its little friend, the helicopter, and it's, whoa, zoom, zoom, zoom. So it goes like a few meters up, and then it goes, meow. And it actually traveled 50 meters to the side, and it went off this field of view of Perseverance. So it's like, oh, see you, dude. I'm going over here. So this was.
But wait.
What?
I said, but wait.
It'll come back.
Yeah.
So this is the third flight. The first flight just went up and down. The second flight went up and then turned and then went like, I think it went 2 meters to the side and then 2 meters back and then dropped. And this one, the third flight, goes up and goes 50 meters to the side and comes back and then goes back down. It'll have 2 more test flights in the next like 2 weeks, but they haven't released what the plans for each of those flights are. I think it's nominally like, how well did this do? How much can we push it for the next 2? But it's pretty exciting that we have a drone on Mars just kind of zooming around. All right. Let's see. What else have we got here? The North Pole of Saturn exhibits what unusual feature? I like this one. I love this feature.
It is objectively the best planet. Just like, did you see my earrings?
Oh, do you have?
Oh, very
Saturn?
nice.
Whoa.
Hey. Oh my God, you have to type things in?
Yeah, type it in. Whoa. People
Good
really
thing I
like
can
it.
spell, maybe. Wait, you can submit multiple ones?
I think so, yeah. If you feel like it, if you're feeling crazy.
I'm not witty. I don't have a fun joke.
Ooh, a hexagonal shaped cap. People are generally in agreement. Everybody knows about the hexagon, evidently. I thought this was a little known fact.
What?
Little known.
This is the coolest fact.
You saw I tried to plant octagon in there just to, mix it up.
That was you?
Yeah, that was
That's
me. Of course.
Ah, Cameron.
Answer.
Misleading.
Wow.
So you're not getting the prize.
Wind. Yes, there is wind.
Hi, chat.
Indeed.
Yeah, so indeed, here's the hexagon on the north rotational pole of Saturn. It shows up, it's shown up since it was first passed by with Pioneer, Voyager went past and saw this above above the pole, and it's not fully understood why it's there. You can reproduce different polygons in fluids when they rotate at different speeds and have a shear layer, so you can produce like hexagons and octagons and triangles at different rotation rates. But it's not super well understood. It's changed color over the last 2 times it's been observed. So it was observed with, as I said, I think Voyager 2 of the Voyagers, and then it was observed more recently with, well, presumably with Cassini, since Cassini was doing its business around there. And it changed. It was like a different color when it was observed the second time, when there was like a 30-year baseline. But yeah, it's just like the motion of the atmosphere. There happens to be this polygon. It's not at the southern hemisphere. It's only of the northern.
Yeah, super cool. Also, still don't really know why.
Hexagons rule. Okay. China and Russia. Oh, I misspelled this in my question. Sorry. Forgive my poor grammar in the question. Are collaborating. You can ignore that have. Are collaborating to build the International Lunar Research Station. What is a likely location for this station or a lunar settlement or whatever? Far side of the moon, good idea. South Pole, good idea. Ooh, maybe I'll put something in here.
Do I have to know like the crater?
I was just about to say, this is brushing up on my lunar geography.
Oh man.
You know what I mean?
I have an answer.
Lunar features.
I know it. I know it.
Well, all kinds of things here. So lots of good options. Tycho. On the moon with 3 exclamation points. I like that response.
That's fair. That's fair.
Lots of good options here. So the suggestion that or the answer that I put here are the lunar poles. In a crater at the lunar poles, probably around the edge. So like, can you guys see my cursor?
Yeah.
So probably like hanging out along the edge of one of these craters. This is the Shackleton crater, which is near the southern lunar pole. And the reason the lunar poles are really good is that when you, I even had a nice, got this exercise ball thing. So when it's rotating around, you know, it has a rotational period of about a month, moon. So that means it's one side of it is dark for like 2 weeks, which is not so good when probably your energy is gotten by solar energy. You don't want to be in the dark for 2 weeks. So if you're at the polar regions, it means that somewhere near you is probably lit up by sunlight for basically the entire period. Whether it's on the inside rim of a crater or the outside rim of a crater, you probably have access to sunlight. So you can set up solar panels there. And what's more, in these craters at the north or south poles, they don't ever get sunlight in them if they're deep enough, just because of the geometry of where the sunlight's coming from. And because they never get sunlight, it means they're super cold because there's no atmosphere to redistribute heat like there is on the Earth. And that means you can get like, it's only like 20 degrees Kelvin, 20 degrees above absolute zero. And in those cold traps, when there's moisture that somehow gets in there, it sticks to it and it freezes there and it stays there indefinitely. So we have shown through observations with a couple of different satellites that there are permanent like ice traps in these polar craters, and we can access those and use those for a variety of things, like use it for water, use it for break the hydrogen, you know, break it into hydrogen and oxygen, use that for breathing, use that for rocket fuel. It's like, you don't have to carry water there, you can just get it there. So people nominally want to plan to have bases or settlements or whatnot there. This is an artist's conception of such a base. I don't think a base is going to look anything like this, but that was some artist thought that was what it's going to be.
Have you seen the show For All Mankind?
Yeah, I've been watching it.
Mm.
I am halfway through the second season. It's pretty good.
Right? Right? Okay.
I'm
Yeah,
not in the know.
you guys
What's
seen it?
the show about?
It's a show on Apple TV, which means you have to get Apple TV, which is another one of these services that you have to pay whatever $10 a month
Fair enough.
for.
I actually have it. I'm surprised that I haven't seen the show
Hey,
yet.
yeah,
cool. All right, then you should watch it.
The premise is that it takes place in the late 60s during the height of the space race between the Soviets and the US. And the premise is that the Soviets were actually the first people to land on the lunar surface, not the Americans. And what are the like geopolitical repercussions of this? Like, how would we have responded to this? How would the Soviets have responded, continuing their dominance in the space race that they had through the early parts? I mean, they were the first people to put Sputnik in orbit, the first people to put a person in the moon or a person in space, Yuri Gagarin. And it's well done. It's well done. So
Sounds
the second,
I like it. I like it a lot.
the first season is late 60s, early 70s. The second season is like 1984, 1983, but it's good.
Got you.
Anyway,
All right. Very nice. Thank you for that. Yeah, I think that'll be on my watch list now.
yeah, it's pretty cool. And we were not paid by Apple TV to give so much.
Oh yeah. Okay. So when you said Shackleton Crater, I was like, oh, that's the show, and that's what the chat is saying too. Yeah.
Yeah.
Yeah, that's where they went.
Yeah.
And can I just give a real quick shout out to this show, because in the show, spoiler, the Russians put a woman on the moon, and then all of a sudden now there are female astronauts in NASA, and it was like this big push like for equality and things like that. And I really appreciate then they talk about like ramifications of all of that and how they were treated and all this other stuff. And so while it all is fictional, it is all very true to like how situations are for women in industries like this. And so I appreciated all of the kind of hard conversations and hard moments that they show for these women who are doing these things.
And not just women, but minorities in general. Like one of the main characters is a African woman. One thing I would note though is the Soviets did put the first woman in space, Valentina Tereshkova, and she beat the Americans. Like the first woman in space in the American side was Sally Ride, who wasn't until like mid 80s, and I want to say Valentina Tereshkova was first woman in space in like early 70s. So the Americans really fell behind on that, which is a bummer. But yeah, so the show kind of showcases, highlights the divisions of reality as well. But anyway. All right, back to the trivia. Next question.
Oh yeah, Cameron, you shouldn't have us talk during this. We'll never get through.
I mean, that's what it's all about. Stars come in a variety of colors. What color is not represented in the colors of stars? Oh, wow. Somebody goes right to it.
Oh my God. Wait, what do you mean?
I mean that when we look up in the night sky, you hear about like red dwarfs, blue giants, white dwarfs. There are all these colors.
But the sun is green.
What color do we not have represented in the color, like the bulk color of a star?
Are black and white colors?
Ooh, chartreuse. Ooh.
Yes.
Purple. Okay, that's.
Am I overthinking this?
No. Did you put chartreuse?
No, but I don't even know how to spell that, so I'm glad I didn't try.
Right.
I hope someone in our audience is drinking chartreuse. That's a fine.
Oh God. I hope they're not.
Octarine.
I'm overthinking this because I don't want to give all of it.
No, talk. Say what you say. What do you think? No, it's okay. It's like our general conclusion. Oh, there's a brown in there, but generally people are in agreement that green. Ooh, turquoise.
Turquoise, I like it.
That's nice. That's nice.
Okay. Well, so what I had in my answers was green or purple. There are no purple supergiants. And the reason for this, well, first, Rebecca, say what you want to say, because it sounds like you've got this all ready to rock.
Oh, the sun is green? Is that what you meant?
Well, the sun
peaks in green.
Yeah.
Yes, the sun peaks in green, but when we
So the
look up
sun's
at the
green.
sky, it does not look green.
Okay, well, that was my question. Technically, green is the color, just because you don't see it that way.
No, but green is the color of the peak wavelength, but it's not the color of the aggregate of all the colors that make up.
Sure, but that doesn't mean it's not represented. So I just have an issue with the way you phrased your question.
Oh, I see. Okay. So throw this one out because of poor phrasing.
Yeah.
Well, so for people, just to make sure we're all
people who are like this crazy person, the sun is not green.
On the same page. Okay, so we've got all these different colored stars. You've heard of blue supergiants or red giants, red dwarfs, brown dwarfs, white dwarfs, lots of dwarfs. But you've never heard of like green stars, and that is because this is called a black body curve, which essentially means just like the distribution of wavelengths of light that come from something that is just purely an object that's heated up to a certain temperature. So if I take my arm and I heat it up to 1,000 degrees or 1,500 degrees, it's going to start glowing. I'm not going to do that because I like my arm. But any object can heat up, and when it gets to a certain temperature, it will have a characteristic spectrum of light that comes off of it that's described by something called the black body spectrum. And that spectrum looks something like this curve. The x-axis is wavelength. So redder is to the right and bluer is to the left. And then the y-axis here is like the intensity, the amount of light that's coming from each of those colors. And so for cool objects, like, if I heated my arm up to only 500 degrees, the peak of this spectrum would be over here in the red or the infrared. And as it goes to higher and higher temperatures, it drifts to the left. And then it'll peak in the orange, the yellow, the green, then the blue, then the purple, and then finally in the ultraviolet. If it's really, really hot, if it's like 100,000 degrees, it's in the ultraviolet. But there's still going to be light that's coming from all of these wavelengths. And so the sun, this is the distribution of light that comes from the sun, which you can see the peak of that distribution is in the green, just as Rebecca said. But because we don't just see the peak light, the peak wavelength of light that's being emitted, we see the aggregate of all these things and they blend together, and our eye perceives that as, yellowish white. Green is just too narrow a band for us to be able to, it would have to be like this super narrow peak to be able to pick out the green. And we just don't see that with thermal objects, only with things like LEDs that are a really, really narrow feature. So you can't get green and you can't really get purple. Purple is also super narrow, but you can get blue and you can get red and you can get yellow and that sort of thing. Does that reach your level, your threshold of like okayness?
I'll allow it.
Okay. All right. As we look at objects, this is totally consistent with the talk that you just gave. As we look at objects farther and farther away, we're effectively viewing them in the past because of the finite travel speed of light between when that light was emitted and when it gets to us. What is the oldest thing that we can actually see in the universe? See using electromagnetic waves like light.
I'm going to wait for other answers before I put one in.
Yeah, same. Betty White.
Really likes Betty White.
Betty White is a great answer.
That is hilarious.
Tumba. What's tumba?
Very nice.
Cosmic background 3K. Betty White has a couple of votes there based on its size.
Ooh. These are all really good answers, you guys.
Yeah, this is good.
Yeah.
I like it.
I think CMB means cosmic microwave background.
Yeah, so several of these are the same answer. Just
Indeed.
Queen Elizabeth.
Queen Elizabeth.
She is quite old. She's like 90s now. And her husband just passed, what, 2 weeks ago?
Yeah.
She is
Yeah,
the
David Attenborough is getting up there too.
Yeah, he is.
I think him and the Queen are only like a few years apart, right? In terms of age, something like that.
Well, I mean, isn't she his mom?
What?
Wait,
Duke of Edinburgh, is that Charles?
no. I said Sir David Attenborough.
Oh, Sir David.
Yeah.
What kind of rumors are we starting
I was
tonight?
like, yo.
Oh, that's quite a rumor. You heard it here first, people.
Yep, yeah.
Richard Attenborough is the son of Queen Elizabeth II. Yeah, so the answer indeed is the cosmic microwave background. This is an image of it taken using the Planck telescope. There have been a variety of different instruments to kind of deduce the structure of it. WMAP was one. There were earlier ones in the 70s and 80s, but Planck is kind of the most recent. And the blue and red colors here represent intensity from, is it intensity or is it, oh, now I'm going to mess it up. What do you guys think? The blue and red colors, I thought they were intensities, but maybe they're temperatures. I thought
it was 10.
Yeah, maybe it is.
I want to say temperatures.
Yeah, I think you're right. I think it's temperatures.
Mm-hmm.
So this is after removing the galactic component. And so, yeah, the reason that this exists is, remember we were talking earlier about the Big Bang and the universe and the early stages of time in the universe. And it was so dense and so hot that the photons, the light that's flying around, were really, really energetic. They were like, gamma rays and X-rays flying around. And every time, but there were also protons and neutrons and electrons hanging out. And every time a proton and electron would combine and form a hydrogen atom, they would almost immediately get struck by a high energy photon that would ionize them, that would separate them. And this was just going on. So it was a big soup. But the universe, remember, was expanding. And as it was expanding, it was cooling and the density was dropping. And so eventually it just reached this stage where as it expanded, those photons were redshifted. So they were going to lower and lower energies. And at some stage, it reached the stage where those photons were no longer energetic enough to, when they slammed into a proton and an electron in the form of a hydrogen atom, that they would ionize it. And that is called the surface of last scattering, which is what we get this cosmic microwave background from. That was the state of the photon distribution at this period, which is what? Redshift of 1100, which is about 380,000 years after the Big Bang. So that sounds like a long time because you're like, oh, Queen Elizabeth is like 100 years old.
Apparently she's 95, according to the chat.
Oh, she's 95. Okay.
Basically 100 if you round up.
Yeah, order of magnitude.
380,000 is a long time. But then compared with like the current age of the universe, which is like, almost 14 billion years, is not such a long time. So there is no way for us to get light earlier than that because all the photons are flying around, running into the hydrogen nuclei, or the hydrogen atoms, and the protons and the electrons, and it's just a big soup. And there's no way of getting information from before that time from electromagnetic radiation. So this is like, it's like a wall.
So light. So hence the C in your question.
Hence the what?
The C. What can we see in your question?
Exactly. What can we see? That's right. I have to be careful in my wording, or I'm going to have some semantic person who says,
listen, if you can't make the test proper, then you can't really grade them on it. That's all I'm saying.
I agree. I should have had you proofread everything.
You should have.
All right. Let's see. Next question. Ooh,
Mm.
Rebecca, how long ago did GNZ 11, the most distant galaxy studied, exist? Well, okay,
Such a great name.
I know. So who named it? Did you name it?
No. I don't know who named it, but I feel like the Relics team was the one who found it. So there's a collaboration that's called themselves Relics, which stands for something because it's an acronym, because everything in astronomy is acronyms. And I believe it was like a catalog number, and then they just took out the number since they decided to be, way more cool than the rest of us who use all of our catalog numbers.
Got it.
For things.
But the Z11 means it's at redshift of 11.
Yeah. And Goods North is a field. It's an area of the sky that's been studied a lot, especially with the Hubble Space Telescope. But we also have ground-based telescopes that have stared at it. We have the Spitzer Space Telescope, which is an infrared telescope, RIP. A lot of telescopes have pointed at the same spot on the sky to study it at multiple wavelengths, so we can see different parts of galaxies, or we can study different things in the universe. And Goods North is one of those fields because it was originally stared at for a long time with Hubble as part of the Goods program, which was like Galaxies and whatever acronym that stands for. And it was the northern field instead of Goods South, which is the southern field. And those are two of the Candles fields, which is another acronym, which is just out of control, really.
So these are just
Acronyms within acronyms.
I know they really are. Nested acronyms are not great.
All right. So it looks like people are generally in agreement that this was a long time ago.
A lot of time ago.
And people are saying more than 13 billion years ago. And indeed, that is the correct answer. This is an image that's zoomed in on this distant, I guess this is the Goods field.
This is the Goods North field. Yeah, this picture.
And so that's a weird looking galaxy, that little blob.
Right? They're just messy little balls of gas and dust and stars that just happen to be gravitationally bound, which is how we define them as galaxies.
So they never show any kind of disky or spiral structure like we see today.
This early, no, we don't, because it's so volatile that like the universe was much smaller back then, right? So the universe has expanded, meaning that like there's more space in between things now than there used to be. And so galaxies interacted a lot more often since they were much closer together. And so it takes, there's a really cool video, which I feel like we could find if we decided to try, that shows how galaxies kind of merge into what we would see as some of those famous Hubble images. I'll find it when we do next.
Oh,
question.
yeah.
Yeah, you know what I'm talking about? Yeah. And so like those early galaxies haven't really had time to do that because there's like a lot of stuff falling into them, or they're interacting with other things, or stuff is close enough to them that the gravity is affecting it. And so like they're kind of just a bit of a mess, which I relate to. So,
Yeah, too.
Yeah.
Here's a nice artist's rendition.
Look how cute it is. So actually, can I just point out real fast?
Yeah.
So this artist rendition is what it would look like if you were there, right? So if this galaxy is emitting ultraviolet and like bright blue, these bright stars are big, bright stars that are like forming and exploding and all this kind of stuff pretty quickly. But when we actually observe it with Hubble in the previous image, it looks to be red to us because of the redshift, not necessarily that the galaxy itself is red. The galaxy itself is blue like this and very bright in the ultraviolet. And that is the type of galaxy that we're studying that looks red to us here from Earth because of this whole redshift thing. Jason, you see my shirt?
Oh,
Sorry.
Jason Achilles is on?
Jason's here. Yeah.
Nice. Hello, Jason. Jason is one of our past guests and a rock star who played some of our shows in person back when we were in person in a bar.
And speaking of Mars, he also put a microphone on the Mars rover.
Yes.
What?
Yeah.
All right, next question. Star Wars planet Tatooine orbits two stars.
Ooh.
What are their names? There's always a Star Wars planet question.
Why is this the Star Wars question you picked? Their names?
Oh, and I have a piece of news. I'm excited to announce that I just got the vanity license plate, Tatooine.
Oh,
I'm so excited. California Tatooine. If you see it, it's mine.
oh, of course you did.
Incredible.
Yeah, about that. Ooh, Tattoo 1 and Tattoo 2.
I like it.
I like that a lot. Yeah, this one I have no idea what the answer is. It's been so long since I've seen Star Wars.
That's okay. They don't actually.
They don't tell you.
They don't say in.
Oh,
No,
Luke
this
is
is
not
just some
fan-
Cameron nonsense.
Fantastic.
John Luke and James T. Kirk.
Oh
Excellent.
no, you're gonna make his brain explode.
No, that's okay. I have a guy, one of our former speakers and I are going to do a science of Star Wars and a science of Star Trek astronomy on
Oh,
tap.
I like it.
Probably in July, but I need to double check the date with him.
Okay, cool.
So that'll be fun. Ooh, Luke and Leia. I
Luke
like
and
that.
Leia's a good one.
Yeah. That's
All right. So the answer is indeed Tattoo 1 and Tattoo 2.
Nice.
I kind of like that because it's like Tattoo 1, Tatooine. But yeah, so obviously
Why
this
isn't it
science
alpha?
fiction- What's that?
Why isn't it alpha?
So that's something I wanted to bring up is the brightest star in a constellation is the alpha star. So for instance, the brightest star in Centaurus, the Centaur constellation, is Alpha Centauri. People have heard of Alpha Centauri, but you can do this with any constellation. The brightest star in, Botus is Alpha Botus. The brightest star in Gemini is Alpha Gemini, so on and so forth. Normally with stars, it wouldn't be 1 and 2, it would be A and B. So for instance, like the brightest star in our sky, not Star Wars universe, but our sky is Sirius. And Sirius is actually a binary system. There's Sirius A and Sirius B. Sirius B is a white dwarf that orbits around, the center of mass of Sirius A and Sirius B. Honestly, when they wrote this, they should have made this Tattoo A and Tattoo B. But we'll give them a little bit of slack, George Lucas. That's okay. But there are in fact circumbinary planets like Tatooine, where a planet, look on the right side here, the planet orbits around 2 binary stars that are orbiting around each other. And there are like 100 cases of these things that have been discovered in exoplanets that we've found, which is pretty sweet. You can also find these sorts of systems where there's a planet that orbits this star and maybe a planet that orbits this star, and then the stars orbit each other. But this is more like the Tatooine-like system. So yeah. But I'm not an exoplanet guy. So that's as far as I go.
There are planets. End conversation.
All right. Ooh, here's an Evan question. Why are population 3 stars called a theoretical population, whereas population 2 and population 1 stars are not?
Wow, that's a great question.
None been found. Very concise. Low metallicity. Always back to the metallicity. Everybody knows metallicity.
Astronomers were like, meh, metal, done. Don't.
Yep, metal.
Metal.
They're all the same, right?
Big Bang didn't make it. It's the metal.
That's right.
Lithium skates by a little bit.
Yeah, just a little bit though. Just a little.
Just occasionally when we remember.
Too old. Ooh, ageism. Yes.
Whoa.
Good questions. Good questions. Are there, Evan, are there any pop 3 stars that would have survived to present?
Possibly. So potentially. So I'd have to imagine if they were like incredibly low mass, right? To the point where you have lifetime, main sequence lifetimes of like trillions of years, and potentially But the chances of actually observing those even in the neighborhood would just be, it's just very, very, very low. But in terms of like so the answer is most likely not for population 3. And more importantly, for this question, of course, we haven't observed any population 3 stars. So that's why they indeed. Yeah.
Not too old or too fat. As people,
Yeah.
The chat said they're dead, Jim.
They're
And
dead.
that was great.
Yeah. Yeah, nobody's observed them because they probably remember. Yeah, Evan was talking about they tended to be really massive. Massive stars burn their fuel really fast and explode really quickly. So they probably blew up really shortly after they were formed, and we just don't have any around that we can see. Maybe maybe the James Webb Space Telescope, maybe be able to see one. Maybe.
We thought so. We hoped so, but I think the more like simulations and stuff that we've done, we are being cautiously not optimistic.
This is an image from one of those simulations performed by some of my good friends, Matt Turk and John Wise and Tom Abel, of a population 3 star from, I don't know, this is from like a decade ago. But yeah, we haven't seen them yet. Just have simulations. All right. What are the 4 most abundant elements in the universe? I give you 4 because the first two people are like, ha, I know those first 2.
4?
Yeah.
Really?
But
What's the 4th one?
Yeah, exactly.
Who counts that high?
That's why I went 4 down.
Wow, you're rude. Okay, let me see.
Yeah, that's right. That's right.
Oh my god, and I have to type it. I don't get a tick.
Let's see. Think.
Air, earth, fire, and water. I think.
I like it.
Yeah, that's what's up.
4, 5. Wait, what are the stones from the Infinity Stones?
Oh, I don't know.
Those
I
would
was
be
just
good.
thinking of like the platonic elements.
Right.
But bubblegum is in there. Unobtainium.
Yes.
Oh, that's nice.
You guys are way funnier than us. I appreciate you. I just want you to know that. I wish I could make jokes. I'm like, oh, science.
Right. Love
Yeah,
this
that's a
energy.
good question. I don't remember what all the Infinity Stones are. There's like the Mind Stone and the
Power.
Stone and the Power Stone and the
Soul.
Time. Dr. Strange. Time Stone.
Oh, that was a good one. Mind? Isn't that vision?
Oh yeah, I think you're right. The Mind Stone. Ooh, I don't know him. That's a good one.
That's a really good element. I like it. Oh, the chat's got some more for us.
So it looks like if you look just like at the size of people's numbers, there's hydrogen, helium, lithium, oxygen, carbon are the biggest ones.
Yep. The
Is that
chat
what
added in
is?
silicon and iron.
Silicon and iron. Okay. Well, indeed, hydrogen, helium, oxygen, carbon are the big four. Big four. Yeah, hydrogen and helium were the bulk of which were created in the Big Bang, and then oxygen and carbon were almost entirely due to core collapse supernovae. So the supernovae, like what Evan was discussing earlier, when these massive stars, they run out of energy production in their cores, holding them aloft, and then they collapse and they boom and fling out their nuclear fusion products into the world.
There's a really cool periodic table that shows all of the elements, but as like colored to show where they come from. Yeah. And so things are like the Big Bang or supernova, or like how the periodic table is normally colored versus like how it's colored based on where they come from. And that's a really cool graphic of kind of showing where we get our elements from and why some of these are more common than others.
Absolutely. I should dig that out here.
Yeah, we keep saying we'll show you things, and then
I'm just like
we're just stalking now.
You know.
I'm just gonna do All right. Ooh, I think this is our final question. Where was the first flight conducted on another planet? Because people might say Ingenuity on Mars, which
They
happened last,
might.
very exciting. And that might be right, but it might also not be right.
Do you mean like non-Earth?
I said another planet.
Like planets don't include
Earth.
moons.
Oh, good question. Good
Yeah,
question.
because that's where my mind was going.
Right? So like how are you defining planet here?
That's a good question. Well, no, I don't think the moon would be considered another planet. But
Okay.
Okay.
that also raises the question of, were the Apollo missions actually flights? Right?
I mean, is it rocket propulsion
Yeah.
versus like propeller? Like, how are you? Like airplanes
Right.
fly with jets versus helicopters that fly with propulsion.
Yeah,
So like,
this is a good question. I don't know. I would think that something that's on a ballistic trajectory that isn't like interacting with the atmosphere in order to generate lift is not necessarily flight. It's more like a liftoff. It's like
it's a rocket.
I don't know.
Rockets don't fly.
Some engineer would say you're wrong.
Yeah.
And I'd probably
We apologize to all of the engineers watching this.
Yeah.
Right? See, the chat's confused too, right?
Right.
Yeah. Well, I'm glad. I wanted to make this kind of a tricky question.
Clearly.
That's fair. You know, mission accomplished. It's really cool. Really cool. I like
I'm
it.
not even gonna answer it now.
Malice.
Whoa, what is that answer?
I don't know.
Master.
It's like somebody just.
Did someone break their keyboard?
Is that another language?
I appreciate that
Is
it
it
has a
so?
lot.
I would love to know.
The accents make it all very exciting.
Yeah.
Right?
Cameron, I'm gonna need you to pronounce that one for us. You're very
Yeah,
good.
please.
9762 Gakuno Homdema. Homdema.
I don't think you got
Nice.
all the accents right.
I don't think I did.
Fair enough. I'm all for it.
Yeah. So kind of a tricky question. I appreciate that everyone didn't like look this up on Wikipedia and then put the answer. The answer is in fact Venus.
Haha.
So no shame here. I didn't know this until I was looking around online for this, associated with the Ingenuity launch. So everybody's been like, Ingenuity is the greatest, and Ingenuity is super cool.
It is super
We're launching a
Indeed.
freaking
Indeed.
helicopter on the surface of Mars and testing it out. But it is 35 years later than the first flight on another planet. So the Russians, I'm sorry, at the time, let's see, 1985, it was still the Soviet Union. The Soviets sent missions, a bunch of missions to Venus. I think it was largely fueled by the fact that they didn't want to be seen as having continued to compete in the realm of trying to get stuff to the moon when we already got and landed people on the moon. So it was like, we're just going to bow out of this and not look like we lost the space race. So they started doing a bunch of stuff on Venus, which is super cool and interesting in its own right. And they sent a couple of missions called the Vega missions that put helium balloons in the atmosphere of Venus. And there was the Vega 1 and Vega 2 missions that were launched in 1984, and they reached Venus in 1985, and they had these helium balloons that while it was descending through the atmosphere, it like sent a bunch of helium, it depressurized helium into a balloon that was, like 4 meters across, 3 meters across, 4 meters across. And then it had this gondola with the payload had a pressure sensor, a temperature sensor, an air density sensor, and it just let it kind of hang out and sail with the breeze. And it sailed for like a couple of days just on the atmospheric motions and recorded this stuff and beamed back the information. And so much of what we know about the Venusian atmosphere came from these missions in 1985, which is super awesome. It was just hanging out at like 50 kilometers up in the atmosphere, just like sailing away.
Just cooling out. Wow, that's amazing. That's pretty cool.
Yeah. So obviously different than a helicopter, but cool in its own right.
Right.
Mhm. Was this part of the same like program that actually put the actual lander on Venus?
Yes, that's right. So this also, in addition to the balloon, there was a component from that same mission that went all the way down to the surface and took data as it descended down to the surface. They had a series of different probes that went through the atmosphere and took samples and then took samples on the surface. Venera, and then this is Vega. But you know, the problem is the pressures and the temperatures are so high down at the surface that things melt within like 10 hours and you're like, oh,
It's kind of like actual hell.
it's pretty
Yeah.
rough down there.
Yeah.
It's pretty rough.
Tough.
Not so great. Runaway greenhouse effect.
Runaway greenhouse. That's right. But it's super cool. And I should add, I helped with a balloon launch here on Terra this last week. But it was not sailing around half the globe like on Venus. And it wasn't nearly as hot or as dense, but sent a hot air, sent a helium balloon up to like 110,000 feet and took images of the sky.
Nice.
Pretty interesting. So
yeah, fun fact, we do astronomy with balloons.
yeah, it's a much cheaper way of getting above the bulk of the atmosphere so you don't suffer from the problems of the atmosphere than sending something into orbit. So you put it up on a balloon, it goes up for like 4 hours or 12 hours or 24 hours, and then it comes down, and it's a really good inexpensive test bed for a lot of these technologies to be able to do this sort of thing. So pretty sweet.
To clarify, Ingenuity isn't claiming to be the first flight, but the first powered flight.
This was powered flight, and this is not powered. Yes, that's
Jason
correct.
wanted to clarify. Yeah.
Okay. Thank you, Jason. Keeping me honest. All right, and that is it. That is the end of our pub trivia. I hope people enjoyed that without prizes. Hopefully,
You are all winners for sticking around to the end or something.
Yeah. So let's see. Closing remarks. Our next event will be in 2 weeks. Astronomy on Tap in 2 weeks. The topics are a radio telescope on the far side of the moon that's being planned, a couple that are being planned, an existing telescope that is on board a 747 jet that goes into the upper atmosphere and takes images above the bulk of the atmosphere, many, many nights per year, called Sophia.
Sophia is pretty cool.
Yeah, so Sabrina Pagzad is one of the telescope operators for that. She spent 150 nights on board operating the telescope on.
Like you have a plane, right? You cut a hole in the side of it, you stick a telescope in it, and you're like, cool, that's gonna do it.
I'm gonna look at the sky. Yeah, it's pretty sweet.
What?
So that's in 2 weeks. We'll have a stargazing lecture in a month on neutron stars. We will have a all Spanish Astronomy on Tap in 3 weeks. I'm about to put out the advertisement for that. That should be super cool. I don't speak Spanish, so I will not be emceeing. There will be better people than me leading that event, but it should still be super awesome. One of the talks is on black holes in our solar system.
Ooh.
I don't remember what the other talk is yet going to be.
Cool.
And then we will have our next Astronomy on Tap in Mandarin Chinese in a month. We had one last month. We had 8,000 people turn out for it, which is crazy because we brought.
I'm so glad you did that.
And people were like, yes, I want to listen to science.
Nice.
That's fantastic.
So, yeah.
Yeah, we did a Spanish show.
Oh, you did?
It's somewhere on our channel. Yeah, we did. We did a Spanish show at ATX. For anybody who is interested in more astronomy in Spanish, we have a show on our channel. We also, AOT in Bonn in Germany does both English and German. So if you are not a native English speaker, there are other Astronomy on Tap channels in other languages.
Yeah, there's one in Montreal does French and French.
Yeah.
Nice. Nice.
So we're working on it to get more out there.
Awesome.
Yeah.
Well, thank you, fine speakers. Evan, Rebecca, excellent talks. Excellent getting to chat with you guys and share a beverage. And thank you to our audience members for your attention, for your interest in astronomy and the pub trivia. And join us for the next one. Hopefully you'll have fun. And we have all these events in our YouTube channel, all the past recordings of things. So you can check those out from the last like 5 years of us rambling around and yapping about
Has
astronomy.
it been 5 years?
Yeah, oh yeah. Our 5th year anniversary is in 2 months. We're coming up on 70 Astronomy on Tap events.
Nice.
I don't know
You're
what
like
we're
right
gonna
behind
do.
us.
Are we?
I thought you, yeah. Well, we took a break now, so you're gonna catch up.
We'll have to do something fun. I don't know what kind of cool thing we can do to celebrate the anniversary.
We used to launch a new like merch item,
Ooh.
and in fact, we were
Oh.
scheduled to do that with our coffee cups.
Whoa.
Oh, that's
I
nice.
know, right?
That's
so we're
nice.
like sponsored by Odell Brewing Company, which you can't read because the lighting things. And they made us these coffee mugs in March of 2020. We were gonna launch those. So now there's a giant box of mugs that lives in my apartment
Well,
for whenever this ends, and we can do that again.
Say what you want us to offer in merch, and maybe I'll try and make it.
Yeah, that'd be cool.
Yeah. We have
Absolutely.
bottle opener keychains, we have stickers, we have buttons, we have pint glasses, we have coasters. Yeah, if there's anything cool, I don't know. Some people have been like, give us t-shirts. And I'm like, who's gonna wear a stupid Astronomy on Tap t-shirt?
Whoa, Astronomy on Tap ATX has 7 different t-shirts. Thank you very much.
No, that it would be so cool. I would wear it every day.
Oh my
Really?
god, see?
Not
See?
even kidding. Seriously.
All right. No, maybe I'll have to think about t-shirts or hats.
We have hats.
I can't wear a
too.
hat, but if I could wear a hat, I absolutely would wear a hat.
I cannot wear hats. I can't. But we have hats too. These, see, you and I just need to talk about your merch again.
All right. All right. Well, thanks everybody for sticking around. And we'll catch you in 2 weeks on the flip side, I guess. So,
Thanks for having us.
Yes, thank you.
Stay
gotta figure
safe.
how to turn this off. I don't even know how to turn
You go stop on the live.
this off.